At first, they thought they were watching one tornado. They were wrong. Inside the darkness, smaller vortices were racing around a larger circulation. The shape changed by the second. The ground disappeared behind rain, dust, and flying debris. And for a few terrifying minutes, the entire sky around them was moving. May 31, 2013 began with ingredients that meteorologists recognize as dangerous: a nearly stationary front, a dry line pushing east, and intense instability building in the heat of the afternoon. Across central Oklahoma, the atmosphere was becoming volatile. Storms began forming near the boundary where the dry line and front met. They strengthened quickly, developing strong rotation in the middle levels of the storm. The first tornado in the sequence touched down in Kingfisher County and caused little damage. The next storm was different. It moved into richer moisture and greater instability. The circulation tightened. The warning environment changed from threatening to immediate. What formed near El Reno would become one of the most closely studied tornadoes ever observed. The tornado did not arrive as a neat, sharply defined funnel. It emerged within a broad, chaotic storm structure. Rain curtains obscured parts of the circulation. Dust marked the contact with the ground. At times, the most violent motion was not at the center of the visible funnel, but in smaller subvortices moving within it. That distinction matters. A tornado can look like a single column from a distance, while containing several intense rotating winds inside the larger circulation. These smaller vortices can move quickly, widen the damage path, and make the storm's motion extremely difficult to judge from the ground. Near El Reno, the circulation expanded with astonishing speed. The question was no longer simply where the tornado was. The question was, where would its next intense vortex appear? The El Reno tornado became enormous. The National Weather Service identified it as the widest known tornado on record. But width alone does not explain the danger. The outer circulation was broad. Inside it, suction vortices formed, intensified, and moved around the core. Some were visible as narrow, violent columns. Others were hidden by rain and debris. Researchers studying the storm later found a rapid transition from a single dominant vortex to multiple suction vortices surrounding a weak echo hole in the radar data. In plain language, the storm's center was not a calm center. It was a changing structure, surrounded by rotating pockets of extreme wind. The scale of the tornado also created a dangerous visual illusion. A vehicle could appear to be outside the funnel, while already inside the broader circulation. The edge was not a safe boundary, and the circulation was moving faster and less predictably than many people expected. Storm chasers were drawn to El Reno for the same reason scientists were. The storm offered a rare chance to observe tornado dynamics up close. Mobile radars, probes, cameras, and instruments were positioned around the storm. Experienced observers were trying to understand a circulation that was evolving in real time. Then, the storm changed character. The tornado widened. Internal vortices accelerated. Rain obscured the structure. Roads that had seemed usable became escape routes pointing toward the circulation. Among those caught in the storm were Tim Smaris, his son Paul, and Carl Young, whose work had focused on measuring tornadoes and improving scientific understanding. They died while observing the El Reno tornado. Their deaths, along with the deaths of other motorists and storm observers, remain a painful part of the storm's history. This is not a story about fearless people defeating nature. It is a story about how quickly a dangerous situation can become impossible to read from the ground. As the tornado moved eastward toward Union City and El Reno, it produced extensive damage across fields, roads, and property.
The National Weather Service reports that 8 motorists were killed when the tornado overtook vehicles on Interstate 40 and local roads south of the interstate and El Reno. The storm's threat came from several factors acting together: its enormous width, its internal vortices, its rapid structural changes, and the difficulty of recognizing the true edge of the circulation. A person watching the sky could see one funnel and miss another. A driver could move away from the visible center and still move deeper into the circulation. A chase team could have only minutes to discover that the storm's geometry had changed. The most frightening feature of El Reno was not just the wind. It was uncertainty. El Reno was officially rated EF3 based on the damage surveyed after the storm. That rating is often misunderstood. The enhanced Fujita scale estimates tornado intensity from damage indicators, buildings, trees, utility structures, and other objects that can be examined after the event. It does not directly measure every wind speed inside the circulation. Mobile radar told another part of the story. A peer-reviewed analysis resolved low-level ground relative winds above 90 meters per second near the location of several storm chaser fatalities. That is above the minimum wind speed threshold associated with EF5 damage. The two findings are not contradictory. They describe different kinds of evidence. The damage survey describes what the tornado damaged and how. The radar observations describe what the wind was doing in a particular part of the circulation. El Reno became a powerful reminder that a single category cannot summarize every moment, every vortex, or every wind speed inside a tornado. El Reno changed the way tornadoes were discussed. It challenged the idea that a tornado has one obvious center, one predictable path, and one visible shape. It showed how much can be hidden inside rain and debris. And it demonstrated the value of mobile radar, close-range observations, aerial surveys, and careful reconstruction after the storm. For storm chasers, it became a warning about roads, escape timing, and the danger of treating a visible funnel as the full tornado. For scientists, it became a natural laboratory and a reminder that the most important observations can come from the moments when a storm refuses to behave simply. El Reno lasted only minutes, but those minutes changed what researchers thought they knew about tornadoes. May 31st, 2013. El Reno, Oklahoma.